start So bila saya tengah cakap, any question tu you can just unmute unmute and ask question lah. Okay. Today kita nak pergi kepada material selection. Okay. Okay. And we'll start today with case study lah. I will start with case study. Then we will understand what causes this incident. This is a shell and tube heat exchanger. So we'll understand today what causes this. And then we'll go to low carbon steel. Then we will close with another case study lah. Okay, so what is this? This is shell and tube heat exchanger. All right. This is at Australia, Longford gas explosion 1998. Okay, which have 2 fatalities. Okay, 8 injured and gas supply disruption 9 to 19 days. Okay, so let's understand this. What actually happened? So what actually happened? The distillation column experienced liquid gravel. Okay, this is on the process part, so you don't have to really understand the process part. Okay, this led to a loss of lean oil circulation. Okay, this is mechanical basically. This is the one that we want to understand. With lean oil flow, rich oil flash, and the system temperature dropped to minus 44 degrees. Okay, this is the main item. It dropped to minus 48 degrees. Steel that was never designed for cryogenic service became brittle. This is the keyword, brittle, and dropped to minus 48 degrees. So this tells you that this material is actually carbon steel. Okay, carbon steel is not meant for service below minus 40 degrees. Okay, so in this instant, maybe they do not know that this could happen. Okay, so for this case, it drops to minus 40 degrees, and the material became brittle. Brittle is basically like a glass slide. Okay, so with pressure, it will break like glass. Okay, so what happened? Operators saw ice forming on the outside of the heat exchanger, but did not know the danger. So ice forming, this is an indication that the temperature dropped below 0 degrees Celsius, or more than 0 degrees Celsius. So training did not cover the effect of low temperature embrittlement. Okay, so from this statement, you understand that carbon steel has limitation on the lower side of temperature. In this case, for carbon steel, it's more than minus 40 or lower than minus 40 degrees. We cannot use carbon steel. And then what happened in this refinery? The engineer reintroduced hot lean oil about 70 degrees Celsius. So from minus 48 degrees Celsius, with sudden increase of temperature to 70 degrees Celsius, this caused a brittle fracture. And the end of the vessel tore open violently, releasing a vapor cloud ignited at nearby fire heaters and explosion and sustained fire. Okay, tore open, so we can see again. This is the picture of the shell and tube heat exchanger. This is the tip sheet of the shell and tube heat exchanger. Okay, this is on the channel side. So it tore open. Okay, what is the technical issue here? Brittle fracture of carbon steel due to embrittlement from low temperature exposure. Okay, so from this case study, this is the important point: brittle fracture due to low temperature exposure. Low is more than minus 40 degrees Celsius for carbon steel. Okay, this heat exchanger was not rated for cryogenic or even low temperature service. Low carbon steel loses toughness below minus 20 degrees to minus 40 degrees, and no procedure or instrumentation alerted operators of the risk. Okay. So metallurgical findings: the failure in the channel was fast brittle fracture. Okay, and reduction in temperature of the vessel causes embrittlement of its steel shell. Okay, so from the case study, what have you understand so far? This is a very important point. Fatima, any comment? Okay. So actually, this is a embrittlement of steel shell due to very low pressure. So we call this as brittle fracture. Okay. So link to carbon steel. Okay, this case illustrates the temperature limitation of carbon steel. Safe range is above minus 45 degrees Celsius to 380. So below that, ductile to brittle transition happen. Okay, this is an important point. Ductile to brittle transition. It means that at a higher temperature, later I will show the graph. At a higher temperature, it is ductile, but when it reached about minus 20 degrees, from ductile it became brittle. So this is a transition for the same material. Okay, so a brittle fracture will occur without warning the first time the component is exposed to the necessary combination of low temperature, high stress, and critical size defect. So important point also is without warning. Is without warning. You will not see any necking of this material. It will just suddenly break like a glass. Okay. So far, okay? Understand?
Okay.
Okay, correct. So carbon steel. Okay, let's understand carbon steel. Material basically has two family. One is ferrous, more than 50%. The other one is non-ferrous, minus 50%, less than 50%. So in the ferrous family, we have three basically: carbon steel, low alloy steel, and high alloy steel. High alloy steel is actually stainless steel. Okay, then we have a low alloy steel, and we have carbon steel. Okay, what is carbon steel? Carbon steel, a point to remember is carbon steel is having 0.05% to 1.5% carbon. Okay, between this range of carbon percentage, we call it as a carbon steel. But carbon steel also is divided into three. Okay, low carbon, medium carbon, and high carbon. So for your pressure vessel, at your refinery or petchem, we actually use low carbon steel. Okay, we do not use medium carbon steel. Okay, okay, we do not use medium carbon steel, and we do not use high carbon steel. Okay, so the reason is because the higher the carbon is, when we have a higher carbon, the strength is increased, but weldability becomes an issue. It's very hard to weld. It is prone to crack when welding. So we want to limit the carbon content to below 0.3%. Okay. So for Petronas, PTS is also limiting this carbon content to, I think, about 0.24%. Okay. All right. Let's see the low carbon steel properties. So this is the low carbon steel properties. We have manganese, phosphorus, sulfur, silicon, and copper. Okay. For sulfur and silicon, this is considered as impurities. We try to limit this content, but it's always present in the material. Very hard to eliminate to zero. So, sorry, for phosphorus and sulfur. So very hard to limit to zero. And we try to make it very minimum during the steel making. Okay, so for manganese, percentage is around 0.9 to 1.2%. Okay, this is a very good element. It deoxidizes steel, okay, or remove the oxygen from the steel and increase the machinability and hardenability. Silicon is the same. It deoxidizes steel as well. For copper improve the corrosion resistance of the steel. Okay, so the three element is manganese, silicon, and copper. Phosphorus and sulfur is considered as impurities. Okay, but the thing that you need to remember for low carbon steel is this range, 0.05% to 0.3%. Okay, so why do we use carbon steel? It is good weldability because the carbon content is kept at low, okay, 0.3%, and also easier to form. It can be used at low to intermediate temperature. Later I will show the graph. Low means more than minus 40 degrees, not less than that. Okay, adequate strength for typical refinery pressure range. Okay, economical and widely used. So this is not a low grade material. This is a very good grade material. It is economical because it is widely used. it is easily available. It is being produced at mass. That's why the price is lower. It is not to be confused with the lower grade material. Okay. Okay, this is typical low carbon steel material. Okay, all of this is actually carbon steel. Okay, but if it is on a different component like plate, pipe, forging, fitting, bolting, tube, we use a different code. Okay, so when you want to buy a carbon steel plate, this is your choice. 516. We do not call plate as 106. Once you know it is 106, you know it's a pipe. Okay, so for plate, your typical material by default, you will always start with SA516. Okay, this is a good material. Okay, but if your process requirement requires a high strength material than 516, then we can opt for 537. Okay, all right. For pipe, typically we use 106. Okay, but if it is low temperature service like -20 around there, you will use a SA333. Okay, for forging, typical is SA105. But for low temperature service, you use 350 LF2. This is for low temp. This is your fitting, SA234 WPB. W is weldable, P is pressure resistant, B is actually grade, either A, B, C. Okay, if for low temperature service, we'll use SA420. Okay, bolting, this is typical for carbon steel, 193B7 and 2H. So 193 is for your bolt, 2H is for your nut, and 307 is a foundation bolt. Foundation bolt, you can use 193B7, but this will cost, the cost is slightly more. So for foundation bolt, you do not have to use 193B7. You can use 307 grade B. Okay. For tube carbon steel, typically we use SA179. This is for your normal shell and tube heat exchanger carbon steel. We use SA179. Okay, but if it's a higher temperature, then we'll move to 192, or even a higher temperature, we'll use SA210. Okay, so far okay. Am I going too fast or understand?
Okay.
Okay, good. Okay, nice. Okay, low carbon steel limitation is
Sorry,
there.
aku
Sorry,
masuk SA.
SA. Okay, SA ni is typical name for ASTM material. If you see SA, then you'll know that this is a recognized material by ASTM. So that is where it origins.
Ada beza SA dengan SB kan?
SB, okay. SB, I believe SB is a non-ferrous material.
Okay, faham.
Okay, thank you. Okay, so I can share one experience. Recently we have a shell and tube heat exchanger where we change the carbon steel of the tube from SA 179 carbon steel material to SB material. This SB is SB444. Later we'll cover that. SB444 actually is from this family in Cornell. 165. So for material that is ferrous, it is SA. I didn't put it, sorry. SA. For non-ferrous, it is SB. Okay, thank you for the question. So actually we change from low carbon steel here, we change to here. Okay, why we change is because that this material, non-ferrous material, is having a better corrosion resistance than low carbon steel. That is why we make the change. Thank you for the question. Okay, so low carbon steel limitation at low temperature, we have seen the case study from Australia. That is the brittle fracture. Okay, material loses its ductility and becomes glass-like. Typically starts at temperature less than -45 degrees Celsius. This is limitation at low temperature. But we also have, carbon steel also have limitation at high temperature. This is what we call as creep. Okay, so brittle fracture and creep. Creep is a continuous deformation with the same load. It means that although the load is not increasing, but deformation is keep on happening with time. Right? It is time dependent. It's with time. So it typically starts to occur at temperature more than 370 degrees for carbon steel. Okay. All right. So, okay, this is the temperature range of material. Carbon steel is between minus 45 to 400 degrees Celsius. If you have a design temperature, if the process department gives you a design temperature higher than 400, then you cannot consider carbon steel. You need to consider what you call as low alloy steel. This is the low alloy steel, typically for 400 to 600 degrees Celsius. We'll cover this in our next class. Today is carbon steel. Okay. If you need higher than 600, then you go to high alloy steel. High alloy steel is actually stainless steel. Stainless steel have a very good coverage, but the price, it is more pricier. So the coverage is between 600 to 800 degrees Celsius on the high side. On the low side, it can go up to minus 250 degrees Celsius. So stainless steel is a better material, but if your design temperature is not going to be very low or very high, for cost optimization purposes, you go to either carbon steel, start with carbon steel, or low alloy steel. Okay. Okay, before we go to the next case study, do you have any question?
Apa beza ductile dengan creep?
Okay, ductile, okay. Alright. Okay, ductile. Okay, ductility means that the material is able to handle the pressure without without becoming, basically without breaking. It means that if I have a carbon steel material at a temperature of 70 degrees Celsius with a pressure of, let's say, 100 bar, it can still withstand the pressure. But if the same pressure, 100 bar, but the temperature becomes minus 100 degrees Celsius, with the same pressure, this material will break like a glass. Okay, example, if you have seen the movie, apa nama dia? Titanic. During that time, the knowledge of material is not very good. So during that time, they use the material that is prone to brittle fracture. Okay, so when the Titanic sail at the sea at night time, and you can see all the apa yang ice tu, so the sea is actually very cold. So when it hits the iceberg, although it's just grazing the material break. So if the same thing happened to that Titanic vessel or Titanic ship at a different area, which the temperature is higher, then it may not cause the ship to tenggelam lah. Okay, so to answer your question, ductility is the ability of material to withstand the stress or pressure at the temperature. So ductility is good. Okay. The issue is this ductility loses its ductility, become brittle. That's the issue. This ductility becomes brittle at a temperature of around minus 20 degrees for the same material, carbon steel. So when you go to minus 20 degrees or minus 40 degrees or lesser than that, the same material, carbon steel, from ductility, it transition to brittle. So when in the ductility, the same pressure for ductility, it's okay. But if it goes to the same pressure goes to minus, let's say less than minus 45 degrees, it will break the material. Okay, without warning, because it's glass-like. Okay, so the other question is creep. If I'm not mistaken, the other question is creep. So creep, it happens at a higher temperature. So this happened at less than minus 45. Creep happens at more than 370 degrees Celsius. So what happened, this creep, when we have a very high temperature, carbon steel across its borders, it tends to become dia akan jadi start to porous to the border. Okay, so with time, is time dependent. So with like say 10,000 cycles, or maybe I'll do a class on that. So when the times katakan dah setahun, 2 tahun, 3 tahun, so along the border, dia akan start to crack. Even though the pressure still remain the same. But because it operates beyond 370 degrees at a very long time, you'll see that it begins to crack. Okay? Boleh, did I answer your question?
Yes.
Okay, thank you. Okay, any more question before we start to Tesoro? Okay, so any question you just can unmute. We'll go to Tesoro now. This is a case study. This case study is neither brittle nor creep. So this case study is actually on the hydrogen. This material is basically not suitable for hydrogen service. Okay, this is your heat exchanger. Okay, this is all shell and tube heat exchanger. Alright, for E, they put there as fail. So this is the fail heat exchanger. So we'll try to understand this. So Tesoro case study, this is in US, Washington, happens in 2010 with 7 fatalities. Okay, the carbon steel shell was weakened by high temperature hydrogen attack. Okay, so when you see this HTHA, you understand this is high temperature first, and you understand is hydrogen attack. Okay, so 2 elements happens here. One is high temperature, one is hydrogen attack. Okay, a slow invisible degradation mechanism. What does it mean? It means that by inspection, maybe you will not be able to see this degradation. Okay, this is invisible degradation mechanism. Okay. So what happened? Okay, what happened is these hydrogen molecules. Okay, hydrogen has H2N. So one is hydrogen molecules dissociate and diffuse into steel. So dia masuk dalam steel. Okay, because kalau ada crack. Because bila steel tu ada crack, hydrogen tu boleh masuk through the crack into the steel. Okay, and then it reacts with carbon. So hydrogen reacts with carbon becomes methane. So methane is actually a gas. So you have a gas forming inside your carbon steel. So over time, this gas will accumulate, and this gas turns into micro cavities, many cavities, forming fissures and blisters. Okay, over time, micro crack coalesce ni maksudnya dia bergabung lah. And then when dia bergabung, you ada loss of strength, and over time it ruptures. Okay, so you need to understand the mechanism. Hydrogen goes into the steel because there is a crack. Okay, then hydrogen fused with the steel becomes a gas, which is methane, and this gas coalesce. Coalesce maksudnya bergabung-gabung, campur, and then this causes the crack. Bila ada crack, bila ada pressure, bila ada temperature, this crack akan propagate. Bila crack propagate, dia rupture. Okay. So key point from this case study is the damage concentrated at non-PWHT well. So it started with the well. And this well is required to be PWHT, but it was not. Where residual strength very high. Residual strength is coming from the welding process. For carbon steel above 38 mm thickness, we need to do PWHT. Or if it is above 32 mm, we need to do a preheat. Okay. Why do we need to do that? It's because we want to reduce or eliminate the residual stress. For this case, we didn't do, or they didn't do the PWHT, meaning it is having a residual stress and it damage. When it damage, this is the mechanism happen because of the damage well, because they didn't do PWHT. Failure initiated at this well and propagate across the shell. Okay. So far boleh faham? HTHA, high temperature hydrogen attack. Okay. Alright. So kalau tak faham, just unmute. Okay. Now let's try to understand this curve. Don't be intimidated by this curve. This is a Nelson curve. Okay, what is a Nelson curve? Basically, Nelson curve, we have several Nelson curve for several other material. So what we are seeing, this curve is for carbon steel. It is it's not very complex. You can see this is the line. This is the line of the curve. Then we will need to plot. What we are plotting is actually the design temperature here, the temperature here, and also the hydrogen partial pressure. So if so if we plot, if let's say that the dot is higher than this line, let's say it is around here, then we say that this material at this temperature with this hydrogen partial pressure is prone to HTHA. So we cannot use that material because it is prone to hydrogen attack. If it's below this curve, let's say here, then we see that it is not prone to hydrogen attack. Okay, but for the case of Tesoro, the temperature and also the hydrogen partial pressure is actually below this Nelson curve, but still it happens. Okay, so still it happen. High temperature hydrogen attack still happen, although by temperature and by partial pressure, it is below the Nelson curve. So CSB recommends, or CSB says that this curve is not conservative enough. So for carbon steel, they draw a new line. CSB, draw a new line. This is the line. So their recommendation, okay, their recommendation is, in order to use carbon steel, in order to use carbon steel, it needs to be below 400 Fahrenheit. Above 400 Fahrenheit and above this 50 PSIA hydrogen partial pressure, we cannot use. So this new line is being introduced. So whatever is here, we cannot use carbon steel. Whatever less than here, we can use carbon steel. And we need to do PWHT as well. Okay. Boleh faham ke? Nelson ke?
Faham.
Okay, Jun. Alright. So what is Nelson curve? It is a set of curves showing the safe operating limit temperature versus hydrogen partial pressure for different steel exposed to hydrogen at high temperature. So in short, it tells you when your steel will start to suffer HTHA. So the basic idea is each curve represents the boundary between safe and unsafe. So what is the boundary? A point below the carbon steel curve considered safe. A point above the HTHA, a point above the curve, HTHA can occur. So below here is safe. This is not safe. But for this particular case, for Tesoro, CSP recommends a new line here. Therefore, below the new line is safe. Above the new line is not safe. Okay. Any question?
So if they say above the Nelson curve, they need to change into other material lah.
Correct. Yes, you're right. So this other material is no longer carbon steel. We can consider low alloy steel, which we will cover next class. Okay. So as engineer, one of the things that we need to keep in mind when we choose a material, one of the things that we need to keep in mind is this material needs to be inherently safe. Inherently safe. For carbon steel, it needs to go to PWHT. What happened if we didn't go to PWHT, then we'll have issue with HTHA. But for low alloy steel, also need to go for PWHT. But inherently, the low alloy steel is a better choice than carbon steel. So for this case, in my opinion, what should have happened earlier is that we use low alloy steel rather than carbon steel. Okay. Okay. So let's do a quick recap. So after this, I'll give the quiz. Quiz is about 21 question. For the first winner, the price is 100 ringgit. So good luck to you guys, and everybody that the one that won, please contact me. So we'll recap. Okay. So we have talked about carbon steel. We have understand that this is a case study for Longford explosion. The main thing that we have understood from this Longford gas explosion is actually brittle fracture. Why brittle fracture? That because of this temperature plunge, it plunged to less than minus 48 degrees Celsius. This temperature is no longer suitable for carbon steel. Okay, at this temperature, carbon steel becomes brittle. Brittle is glass-like. Okay. When they do sudden reheat, suddenly they introduce 70 degrees Celsius hot lean oil. Suddenly it expands from minus 48. This is what caused the rupture. So you can see the rupture. This is the tube sheet. This is the channel, and it ruptures. So this is the main thing that we have studied for Longford. Okay. So we have understood this is the carbon. This is the material family. Okay, material is divided into ferrous and non-ferrous. Okay, carbon steel is under ferrous, but what we use in our refinery and petchem is for pressure vessel we use low carbon steel. Why do we use low carbon steel? Because we need to control its carbon content. Okay, if it's more than 0.3%, the material becomes very hard to weld. Okay, so for pressure vessel you need to weld. Long seam and short seam you need to weld. So that's why we limit the carbon content for pressure vessel material to be less than 0.3%. For Petronas, I think it's less than 0.24%. Okay. When do you use medium carbon steel or high carbon steel? One of the example for high carbon steel is actually the spring. For your PSV, you have a spring. For that spring, we are using high carbon steel. Okay. It means that when your spring suddenly broken, you cannot attempt to weld. You need to buy a new spring because high carbon steel you cannot weld. Okay, so this is the material element for carbon steel. Okay, low carbon steel, please understand that 0.05% to 0.3%. Okay, manganese, phosphorus, and copper, this is the good element for carbon steel. Okay, sorry, manganese, silicon, and copper. Manganese, silicon, and copper, this is the good element for carbon steel. Phosphorus and sulfur considered as impurities. So we need to have this as low as possible. Okay, this is your typical material for plate, pipe, forging, fitting, bolting tube. 516, 106, 105, 234, 193, 194, and 179. For low temperature, we'll change. For low temperature, 516 is still okay. 516 is still okay for low temperature. For pipe is SA333, low temperature. Okay, for forging is 350 LF2. Okay, for fitting is 420 for low temperature. Okay, for tube, typically used is 179, but if you require a higher temperature, then you go to SA210. Okay, carbon steel, understand there is two limitations. One is at low temperature, one is at high temperature. Low temperature is brittle fracture, high temperature is creep. Okay, right, this is your range for carbon steel between minus 45 to 400. This is where we are right now. For next class, we'll go to low alloy steel. There are several types of low alloy steel, or we call it as a chromoly steel. So right now we are at carbon steel minus 45 to 400 degrees Celsius. This is your safe range. Okay, so this is another case study for Tesoro. This is basically what you need to understand is carbon steel basically is not inherently safe or HTHA. You need to go to low alloy steel. Okay, especially when you have a micro crack. Okay, understand that hydrogen can diffuse into steel, forming gas, which we call methane, and this gas will propagate the crack. Okay, this is your Nelson curve. Whatever above is acceptable. Cannot withstand HTHA. Whatever below can withstand. But for this particular case, CSB says that this curve is not conservative enough. This curve need to draw a new line that says that below this new line is what we say as safe. Above this new line is what we say as not safe. Okay. Okay. Any more question? Any question? Okay. So we can go to the quiz right now. The first winner will take 100 ringgit. Okay. Good luck. I will share the pin button. Okay, I'll share now. Okay. Dia masuk sekarang Seconds Start. Good luck to you all. Okay. For class today, Argai tolong WhatsApp saya, PM saya. Nanti kita akan bagi hadiah lah. For others, thank you for joining. Fatimah, Taniah nombor 2, Amirul, Taniah nombor 3. That's it for class today. Okay, then our next class will start with low alloy steel. Before we go, ada apa-apa last question? Okay, kalau tak ada...
Saya nak tanya soalan.
Okay. Panjat. Okay.
Saya nak tanya, kalau macam, let's say lah, kalau selalunya siapa yang, okay, kan kalau macam kita dah tahu macam ada isu dekat type of material kan, terus selalunya siapa yang akan macam buat call yang kita kena tukar material? Siapa yang, kalau macam dekat dalam organisation, siapa yang akan make that decision lah untuk tukar material for that equipment?
Okay. Usually, siapa yang akan menentukan the material in the first place is actually client. Client tu maksudnya client boleh jadi client own engineer, client own material engineer ataupun client appointed material engineer lah. Mungkin by client punya macam consultant ke macam tu. So dia dah tentukan material lah. So client dah tentukan material, responsibility is by client for the material. So kita ikut. Tapi kalau kita dalam the course of kita punya engineering, contoh MMHC kan, MMHC dia check, lepas tu from their checking, they say that this material is not suitable. Kalau that material is not suitable due to for whatever reason, so EPCC dia boleh kasih TEQ, technical query, kepada client, saying that from MMC punya experience, MMC punya understanding, this material is not suitable due to for whatever reason. And then client akan review dan client akan bagi jawapan sama ada client agree untuk change the material to what material, or client will jawab yang to stick with the material dengan client punya own answer kenapa. Okay, so untuk jawab soalan tu, pertama sekali client yang menentukan material in the first place. Kalau EPCC say that material is not applicable, not suitable, EPCC akan kasih satu TEQ, technical query. And then by that technical query, klien akan jawab sama ada setuju untuk tukar material ataupun remain with the same material. Tak menjawab soalan ke, Syakina?
Menjawab soalan. Thank you, IR.
Okay.
Lagi satu saya nak tanya tu, yang tu kan tu kalau macam case kita buat new equipment lah. Let's say kalau macam upgrade macam yang existing equipment dekat plant kan. So, yang tu siapa yang akan call untuk upgrade material?
Existing plant maksudnya time tu ada klien ke ataupun kita adalah klien?
Maksudnya macam dekat dalam user sendirilah. Maksudnya
user sendiri.
dia position apa, dia metallurgist ke apa ke?
Okay, faham. So kalau organisation tu klien tu sendiri ataupun user sendiri, the right department untuk menentukan material required to change is the AIM department lah. AIM department is the material department. So material department tu dia akan buat satu study. Then by the punya study tu dia akan kasih dia akan beritahu lah material not suitable, and then four option material available yang boleh ganti that material, and which material yang department tu suggest. Bila department tu dah suggest that material, then basically mechanical department tu akan ikut lah. Other department will follow, but the department to say which material is the material department.
Okay, understand.
Okay. Any other question? Okay, kalau tak